there?
Eating an apple.
Alrighty then.
What was that?
I don't know. My camera's done some wonky things. Isn't that interesting?
Be able to click that. Oh, yeah, I can. Great. Yeah. So this is being run in PowerPoint, right? Okay, great. I should still get animations. Yeah, I think so. And the receiver is here. Soon. Yeah, great. Thank you all for coming.
So audio all checked out, everything?
Everything seems right.
Can they hear me from all the way over here?
And some muted, let me just write to it. Can you ask for whether if everybody's hearing you?
Can everyone hear me on Zoom?
Yes, we can hear you very well, and welcome. And we're very happy to have you here. So you may start and also give us a little bit about your background so that people will know where you're coming from and where you are right now in your career. Thanks very much.
All right. So we ready to get started?
Yeah, Professor Gross is the official, so let's assume that that was a call to begin.
Okay, great. Well, thank you all so much for coming today. My name is Jessica Boles. I'm a fifth-year PhD candidate at MIT right now, working with Professor David Peralt. I currently lead a team of 6 working on piezo-based power conversion. I got my bachelor's and master's from the University of Tennessee. Working at MIT. So with that, thank you all so much for being here, and I will get started.
So if you could make your slides full size, then it would be better for the audience to see. We don't see it this way on the Zoom.
Okay, in the seminar room they are, so we'll make that adjustment, see if we can get that working.
Okay.
Is it presentation mode that you're seeing, George?
Well, what I see is we see about 2/3 of the page, the slide, and then the next slide type of view. It's like a presenter's type of view.
Right. You want to get out of that. Right.
Okay. Yeah. Okay. I think it's fine.
Now it's good.
Okay.
Thank you.
Okay.
Could you move it to interface, please?
Yeah, no.
Okay, hide it. Do more, look at more. Hide.
That'll go.
All right. So with that, I'll go ahead and get started. Now my clicker is not working. Oh, was that me? Yeah, that was great. We're good. All
It
right.
looks good.
Power electronics have enabled modern life as we know it. Many things that affect our day-to-day, where we can go and who we can talk to, vitally depend on power electronics for processing and controlling electrical power. That being said, power electronics are often still the bottlenecks in many of today's most exciting emerging technologies. They're bulky, they're heavy, they're expensive. And so significant effort has gone into figuring out how can we miniaturize power electronics in systems like these. Now, before we think about miniaturization, we need to step back and think about, at its core, what is a converter doing? It's pulling energy in from some sort of source, it's momentarily storing it in passive components, and then it's delivering it to a load in a different form. We repeat this process thousands or millions of times per second. We control it with switches. And when we think about miniaturization, we often refer to power density, which is the power of the converters, the power the converter is sending to the load divided by its volume. And we also think about efficiency, which we need high efficiency for high power density due to thermal constraints. Now, if we take a look at the insides of one of these converters, we see a large proportion of their volumes are taken up by energy storage. I'm going to highlight that in the macro chart here. Traditionally, we use inductors and capacitors for energy storage, but there's nothing that says we have to. In fact, as we scale down magnetics in particular, they decrease in power density capability. Let's take a look at that with an example inductor here. If we take this inductor, the amount of power that this conductor can handle is proportional to its frequency times its maximum flux density times its core area for the flux to go through, times a maximum current density times the window area for that current to travel through with the windings. Okay, so that means just a small increase in volume. We'll scale all dimensions by scaling factor alpha. A small increase in volume gives us a drastic increase in power handling capability. Volume increases by output cubed. Power handling capability increases by output to the fourth because of these two area components in here. Now that's a great thing for high power applications. We can scale up volume a little bit, get drastically more power handling capability. But if we look at that in the opposite direction and we try to scale down volume, we see power handling capability decreases faster, which means power density drops. That's counterproductive for converter miniaturization. So to enable major advances in power density going forward, we're going to have to think about a different way to store energy. Now, one promising alternative to magnetics is piezoelectric energy storage. Piezos rely on the piezoelectric and inverse piezoelectric effects, which essentially mean that when we apply a voltage to piezo's terminals, it induces mechanical stress and strain in the material and vice versa. And through that process, we can strike mechanical resonance, like you see here in this animation. Piezos store energy in mechanical compliance and inertia, somewhat like a spring and a mass. And piezos are advantageous in that they have very high quality factors, which is a good thing for efficiency. They tend to have planar form factors. They may be more amenable to batch fabrication than magnetics. And they provide opportunities for isolation with multi-port regulators. But perhaps most importantly, piezos have very high power density capabilities. Here I'm showing a plot of work done up at Dartmouth, in which on the y-axis, we've got power output capability. On the x-axis, we've got frequency. So output power versus frequency for a few different potential future energy storage components for converters. We've got piezos on here. We've got LC resonators on here, capacitor dielectrics today. And we see that piezos are capable, potentially capable, of very high power density capabilities. This is just for a millimeter cube, by the way. Lots of ideal assumptions going in here. This is pointing to some potential capability there. Now, piezos have been used a little bit more than a decade ago for CCFL backlights. Now, today, those aren't as common. We've got LEDs. They were also used or have been used in energy harvesting applications like this shoe I'm showing here. But overall, piezos have seen very little use in power conversion, and attempts to use them in circuits often result in limited efficiencies. But that being said, the most effective ways to utilize them are yet to be explored. So today, we're going to systematically explore how can we effectively utilize piezoelectrics in power conversion. We're going to start by enumerating different topologies and switching sequences for converters that best utilize piezoelectric resonators. Then we're going to extend that to piezoelectric transformers. And then after that, we'll turn to the piezoelectric component itself and say, well, how do we design the piezoelectric itself for a converter? Now, once we know all of that, we'll begin to be able to evaluate what are its potential capabilities for miniaturization. So to start, before we can build a converter around a piezo, we first need an electrical model for it. This is the Butterworth-Van Dyke model. It's got a static capacitance between the two terminals of the piezo, and that's in parallel with an LCR branch, modeling its mechanical resonance properties. The L is inertia here, the C's represent compliance, and L tends to be significantly greater than C, which gives us a high characteristic impedance. So now that we've got a model for it, we might ask the question, well, what would we like to have in a piezo-based converter? If we could just list out characteristics that would be good for a power converter. Well, if we believe piezos could be our route to higher power density, we'd like to use them in converters all by themselves without any magnetic components. So we're going to assume this source load system you see here to start out. Then we might say, okay, well, we'd like to also have high efficiency behaviors like soft charging of the piezo, which means we'd like to charge and discharge its capacitance through resonance so we can reuse the energy it's storing rather than lose it each cycle. We might also say we'd like to have soft switching in all of our switches, same concept there. We might also say we'd like to have all positive instantaneous power flow, which means at no point are we going to send energy back into the input or bring it back out of the load. We're only going to send power in the positive direction. And we might say, well, we'd like to use as much of the piezo's resonance cycle as possible for energy transfer so we can minimize the energy it's got to store. All right, now, in addition to that, though, the piezo-based converter would still need to be practical. We'd like to be able to support a wide voltage gain range. That's what would differentiate this from switch capacitor converters, for example. And in addition to that, we need to be able to implement it with pretty simple switches. A converter that's got a really high number of switches, it's difficult to argue for because of the complexity it brings. And again, we'd like to do all of that with no magnetic components. So now that we've got the source load system, we can start to think about all the different ways we can connect the piezo in the source load system. And we're going to call each of those connections a stage. All right. And we're going to look at stages from the perspective of the voltage they put across the piezo, or VP right here. All right. We'll first talk about what we call connected stages. All the different stages in which we connect the piezo's terminals to the source load system, such that it's got some sort of combination of VN or V out across it. So there's VN, VN minus V out, lots of different options here. We might also, and these are our energy transfer stages. We might also say we'd like to short the piezo's terminals to create what we call a zero stage. These are important for rearranging energy between the piezo states. We might also leave the piezo open circuited to create what we call an open stage. This allows us to, the CP right here, to participate in resonance, which enables us to soft charge it. So charge and discharge it through resonance to get soft charging. All right. Now, once we've got all these stages, we can start to string them together to create what we call switching sequences, or orders of stages that we cycle through over and over again every cycle to bring energy in from the input, momentarily store it, and deliver it to the load. So we'll go through an example here. And because we want soft charging of the piezo's capacitance, we need to alternate each of our connected stages with open stages to allow that capacitance to resonate. All right, so to start here in this example sequence, our first stage, we've connected the piezo between the source and the load to create a VN minus V out stage. And if the current through the piezo is positive, we're bringing energy in from the input and delivering it to the load. At some point, we'll end that stage and create an open stage. We'll open circuit the piezo, and its current, its positive current, will discharge CP all the way down to 0, at which point we can begin a zero stage. Now, eventually, IL is going to go negative. And when it does, we can start the next open stage in which negative IL now charges CP all the way back up to V out, at which point we can begin this fifth stage here, that's sending energy to the output. And then finally, we can use the remainder of the cycle to charge CP all the way back up to where it began at Vn minus V out. Now we're going to refer to each of these switching sequences by the order of their connected stage voltages. So this one we would call Vn minus V out, here, 0, V out. We're going to use that naming condition throughout this talk. All right, now if we go through the process of figuring out what are all the possible switching sequences now that we could conceivably do with these stages that we've enumerated. And then we can filter them down for all the high efficiency behaviors and practical characteristics that we want. And when we do that, the result is then 5 step up and 5 step down switching sequences, which are shown here. And you can see each of these are comprised of different stages. They support different ranges of gain, but these are continuous ranges of gain that they can support, which again differentiates them from switch capacitor converters. Now, what's important here is all these switching sequences require only the piezo for energy storage. They always soft charge CP and are capable of ZBS. They allow all positive instantaneous power flow, and they support a wide voltage gain range. And I should say that these switching sequences are also capable of practical topologies. So here I'm showing a sample of the topologies that can be used to realize those switching sequences, and all of them require 4 unidirectional blocking switches, which is on par with quite a few topologies used today. And as you can see, a lot of these look like switch capacitor topologies or resonant converter topologies. Some look like something different. These are what are used to realize the switching sequences we derived. Okay, so now that we've got converter implementations, we will need to make sure that we constrain the switching sequences for the high efficiency behaviors we wanted. And we can visualize that with a pair of state planes here. Now, we're not going to go into detail about how to construct a state plane today, but essentially you can consider them roadmaps that the piezo states cycle through over and over each cycle. So down here on the left, we're plotting the inductor current, piezo's inductor current versus Vp, the voltage across it. This state plane is going to give us intuition into how the piezo interacts with the source load system. So these vertical lines we're seeing here are the connected stages, they're constant Vp, and the resonant stages you see on here are our open stages. And you can see that we've constrained for soft charging, which means that the piezo state, or Vp, reaches its next stage voltage before a connected stage begins. We can also visualize how to modify this switching sequence for soft switching, which for this particular case required resonating all the way up to 0.6 E right there. Now over on the right state plane, we're plotting IL versus VC, so the 2 resonant states for the piezo. And as you can see, this state plane looks a lot like a circle. These states are resonating with each other throughout the entire cycle. And so looking at that is helpful then for making sure we're getting all positive instantaneous power transfer, but it's also helpful in that we can look at the proportion of the cycle that each stage comprises to calculate switching times. All right, so now you might say, okay, that looks fancy, but why do we care about what all this looks like on a state plane then with these high efficiency behaviors? The reason is because then it informs what our time domain waveforms need to look like for all of the high efficiency behaviors we want. So on the left, I'm showing the state planes, and each of the numbers at the transition points correspond then to the number dotted lines in the time domain on the right. And so you can see that each of these time domain waveforms are showing resonant transitions. So we're getting soft charging, we're getting soft switching. If we look close enough, we'd be getting all positive instantaneous power transfer. And you can see that with the currents down here. And you can imagine then, if we can only measure one of these states experimentally, like say we can only measure the piezo's voltage, we don't know anything about IL or VC on the N side, we can still intuit what those states are doing based on how Vp increases it or decreases in its slope when doing so. Now, speaking of high efficiency behaviors, we can estimate the piezo's efficiency by first assuming that its current is sinusoidal. We said at the beginning that piezos have high quality factors, and so this assumption is pretty valid for something with a high quality factor. If we assume its current is sinusoidal, we can add up all the charge transfer that has to happen during its connected stages. We can add up all the charge transfer that has to happen during its open stages for resonance, and we can take add all of those up together, equate them to the integral of IL, to get what we call the amplitude of resonance. So it's really just the amplitude of IL. So this is purely charge transfer based. Okay, and this first term here is an energy transfer term. The second term here is a term required for resonating the capacitances during open stages. All right, so we can use that estimation technique then to estimate what are the switching sequence efficiencies that we derived. And as you can see, there's quite a bit of variation between the efficiency capabilities of these switching sequences. It turns out that the most efficient switching sequences spend less time, more time in energy transfer stages and less time in frivolous stages like zero stages and open stages. Okay, so when we're choosing a switching sequence for a given application, within topological constraints, you would imagine that we would choose probably the most efficient switching sequence here. All right, now when we take this highest efficiency switching sequence and we prototype it, this is one of the topologies we showed earlier. This is the same switching sequence we showed at the beginning. At the top, this is our expected waveforms, and here are the waveforms that we see on the bench. And as you can tell, these are quite similar to our expected waveforms. They show all the resonant behaviors we want in terms of soft switching, soft charging, all positive instantaneous power transfer. So this is great news for being able to use these switching sequences to get high efficiency and piezo-based converters. Speaking of efficiency then, this prototype demonstrated the highest efficiencies we've seen so far in piezo-based converters. And so this particular operating region I'm showing right here is a gain range between 1/2 and 1. And when we vary the voltage conversion ratio within that range, we have no drop in efficiency, no penalty in efficiency. And so that's great news for applications in which we need a free gain range of 2 without much efficiency penalty. So you can imagine this being used as like a regulation stage. And I should say that the amplitude of resonance model that we presented earlier predicts this behavior because here we're keeping Bn constant. Sorry. Yeah, Bn constant, and we're varying V out, but we see no dependence on V out in this equation. So the experiments here also validate our amplitude of resonance model. Now, I should say that these techniques have also been used by other groups to get high efficiency in piezo-based converters. So here I'm showing some work done at Stanford and then some other work done at the University of Grenoble-Alpes. And all 3 of these universities, including us, are completely separate. These prototypes, the 2 on here are with different piezos, different materials, different vibration modes, completely different frequencies, 6 megahertz versus 95 kilohertz. And you can see that these sorts of operating modes enable us to get high efficiency behaviors that were not possible before with traditional converter switching sequences. All right, so with that, we've determined how we can build a converter around a piezoelectric resonator. Now we're going to extend this then to piezoelectric transformers. A piezoelectric transformer is essentially a 2-port piezoelectric resonator. It's coupled in the mechanical domain. Now, I didn't show it earlier, but one of the limitations of piezoelectric resonator-based converters is that their efficiency starts to drop for high step-down ratios. That's where a piezoelectric transformer could be advantageous because it provides an inherent voltage transformation. In addition to that, piezoelectric transformers provide opportunity for isolation. So these are possibilities that transformers can enable that resonators cannot. So similar to now, unlike resonators, piezoelectric transformers have been tried in power conversion in the past. Again, they were used in CCFL backlights, but for DC-DC power conversion, they've been met with limited efficiency. So on the left, in this work, the efficiency of the piezoelectric transformer is shown with just a sinusoidal voltage drive. And we can see that it's capable of efficiencies 95, 96, pretty competitive. But when we put it in a DC-DC converter over on the right, our power stage efficiency is somewhere between 60 and 70%, not competitive. So something between there is causing the performance of the whole converter to fall down. So we said, okay, can we apply some of these same principles then to reimagine piezoelectric transformer-based converters? Okay, so we can look at this from an isolated source load system perspective. We can look at it from a non-isolated perspective. We can go through the same process of enumerating different stages and switching sequences for each port With transformers, we look at the port-specific switching sequence, and we can constrain for all the same high-efficiency behaviors like zero-voltage switching, soft charging, all positive instantaneous power transfer, and maximum cycle utilization. We can also constrain for practical characteristics like wide voltage regulation range and simple switch implementations. And we want to do that without magnetic components. Now, something that's different about piezoelectric transformers is we've got 2 ports to deal with switching sequences. Now, we learned from piezoelectric resonator world that we need a 6-stage sequence to be able to support a wide voltage gain range. And so we need one of these ports here to have a 6-stage subsequence. This sequence enables ZBS, soft charging, all positive instantaneous power flow with voltage regulation capability. Now, the other port, though, doesn't need to be a 6-stage sequence. It can be a 4-stage sequence that enables these high-efficiency behaviors, but now it's maximally utilizing the cycle for energy transfer and therefore enables high efficiency. So combining both of these, one at each port, provides the advantages of both with voltage regulation capability across a wide range and maximum efficiency. So if we take this to the same sort of enumeration down selection process, we reach a group of, in this case, 8 isolated switching sequences, each with their own voltage gain ranges, shown here on the right, and each with either a 4-stage sequence at the input or the output, and a 6-stage sequence at the other. And again, these require only a piezo for energy storage, and they're capable of all the high efficiency behaviors we've talked about so far. Now, for the isolated case, these switching sequences require standard resonant converter topologies, like you see here, with half bridges at the input or full bridges at the input, and same at the output. But again, it's a switching sequence we're using that enables high efficiency behavior. Now, if we were to relax this isolation constraint, we would find quite a few different options in terms of topology in here, and many of these are capable of even higher efficiencies than the isolated case if we allow them. Now, similar to the resonator-based converters, these switching sequences vary quite a bit in efficiency capability. And something that's different here is which sequence performs best actually depends on the transformer itself. Now, one thing worth noting is that all these sequences are capable of a range with constant efficiency voltage regulation. So wide gain range with no drop in efficiency, which could be extremely beneficial for wide range applications. Now, when we prototype this with an off-the-shelf piezoelectric transformer, so it hasn't been optimized for this application. But we see the same sort of constant efficiency across the behaviors, which again, could be very beneficial for applications requiring that. We can go through the same process of modeling this with our amplitude at resonance model. And if we were to actually optimize the piezo itself, you could imagine we could achieve much higher efficiencies than 90%. But I should say, this is a far cry from the 60 to 70% that we were seeing earlier, purely enabled by the switching sequences we're using. Okay, now we're going to turn to the piezoelectric component itself. We've enumerated and figured out how we need to use a piezo in a converter for highest efficiency, but now we'd like to actually design the piezo itself for even a higher maximum efficiency. So to do that, we need to think about what we would want to have in a piezoelectric component. And to decide that, if we look straight back at what we said at the very beginning, for miniaturization, we want high power density and we want high efficiency. These are exactly the metrics we're going to use for figuring out what we need in a piezoelectric component design. Now, before we can figure out how to design a piezo for power conversion, we need a model of how it's going to be used in a power converter. So for that, we're going to rely on the same amplitude of resonance model that we've already validated as modeling the converter operation. So for this, we've assumed the highest efficiency sequence here at the bottom. In this model, this is a term modeling its energy transfer stages. This is a term modeling its open stage charge transfer. Okay, so first, let's take a look at efficiency. What do we need in a piezo for high efficiency? To do that, we're going to look at that with loss ratio. Okay, so the proportion of power loss for power out. This directly translates to, inversely translates to high efficiency. So for loss ratio, we can compute the loss in the piezo with that amplitude of resonance model right there. and its resistance. It turns out if we then minimize loss ratio with respect to geometry, let's just say the geometry term G, it turns out that the minimum loss ratio is proportional to only material properties of the piezo. Operating point falls out, geometry falls out because we minimize with respect to it. So this means just by the piezoelectric material we choose, we can get higher efficiency. Now the condition for that then is what tells us what operating point would show us this efficiency. All right, so Q here is mechanical quality factor, K is the electromechanical coupling coefficient. So that's how well it translates energy between the electrical and mechanical domains. So this figure of merit, this can be considered a figure of merit for piezoelectric materials that tells us efficiency capability. So next we might say, okay, well, what about power density? We can again rely on the amplitude of resonance model, and we can take power out of the amplitude of resonance model and rearrange it to be a function of everything else. Okay, so this is still the amplitude of resonance model here. Now there's a few different ways we can maximize power density. Okay, so I'll go over those in a second, but the general idea here is we're going to maximize some sort of density metric with respect to another geometry term that we'll call L. One way we can maximize density is looking through at volumetric energy handling density. So we can consider this power density normalized to frequency. Why would we care about that? Well, frequency dictates a lot about our control and power converter requirements. So the higher power density we can get for a given frequency could be a good metric to use. And so when we do that, we find that the maximum volumetric energy handling density is a proportion of only material properties, epsilon and the frequency constant here, and this normalized amplitude of resonance, which we'll get into in a moment. Another metric we might look at is areal power density. This is the power output divided by area. That could be important for applications in which your footprint constrained. Same principle here. The maximum is a function of only material properties and this normalized amplitude of resonance. So these figures of merit are in terms of only material properties and this normalized amplitude of resonance. Operating point information has disappeared. So again, this is a material property thing. Now you might say, well, what's that normalized amplitude of resonance? It turns out if we go through all the math, we can relate this normalized amplitude of resonance to maximum electric field or maximum stress, which are both material properties. That comes straight from the constitutive relations for the piezoelectric material, as well as whatever boundary conditions we've imposed. Now you might say, okay, that's fine, but a lot of times power density is limited by loss, which is true. We can do the same thing with loss density. If we assumed a fixed loss per electrode area, in this example up here, is thermally manageable, meaning like we're going to extract most of our heat through the electrode area, we can then relate that directly to this normalized amplitude of resonance. So we can insert whatever sort of thermal constraint we expect to be able to handle there. So then this normalized amplitude of resonance is again based on material properties, or in this case, a loss density assumption. Now it's worth noting that these figures of merit showed us what we need in terms of piezoelectric material for efficiency and power density, but they also showed us geometry conditions for achieving that. Okay, and it turns out that the geometry condition for minimum loss ratio and the geometry condition for maximum power density are orthogonal, which means we can design a piezoelectric resonator for both of them. This will become important as we start to design resonators. But before then, we can use these figures of merit to then compare different piezoelectric materials. Here I'm showing several different materials of hard PZT. PZT is a very common piezoelectric material for other applications. On the left, I've got power density figure, aerial power density figure of merit. On the bottom, we've got maximum efficiency figure of merit. You can see there's a wide variation between these different materials, different versions of the same material. Now, what I've also shown on here are contour lines that correspond to loss density. I should say this calculation has been in terms of the maximum E field allowed, but I'm also showing contour lines for maximum aerial loss density. The reason why that's important is for a given thermal management scheme, then we can drop down the power density capability directly onto that contour line to see what we can realistically achieve. And what this is showing us then is that it's high efficiency that's going to enable us to get high power density if we're loss density constrained. And that aligns with our intuition of how high power density can be achieved. Now, in addition to that, this is some of our most recent work. We can take a look at other piezoelectric vibration modes. Okay, so piezoelectric resonator has many different ways it can vibrate, depending on its boundary conditions and its polarization direction and its electrode placement. Some of these modes are extensional modes, some of them are shear modes, some of them are radial expansion modes. And as you can see, there's quite a bit of variation between the figure of merit capabilities for these different modes. Some of these capabilities are, or modes are capable of higher aerial power density, but it also turns out that if we switch to look at volumetric energy handling density, quite a bit changes. So depending on what constraints are designed would dictate then what mode we need to use here. All right, now we've validated the figure of merit for efficiency experimentally. Here we've got quite a few different piezoelectric resonators, different shapes, different modes, different materials. And if we take a look here, we see that the estimated loss ratio for the piezoelectric resonator tracks well with the total power stage efficiency. And so that validates these figures of merit as a important metric for helping us design one of these, but it also attests to this loss ratio below 1% for a lot of these piezoelectric materials. Okay, so now that we've evaluated circuit topologies and operating modes for resonators, we figured out how to design the resonators themselves, we're in a position to be able to evaluate the potential capabilities. So first, I want to illustrate an example paper design. If we were to take an arbitrary set of operating specs, okay, so arbitrary voltage or power, we can take one of the highest efficiency, or I guess higher figure of merit materials from our chart earlier. We can use the geometry conditions from our figures of merit for maximum power density and maximum efficiency to design a resonator. Then we can compute what its model parameters are. We can simulate it in LT Spice to confirm that we get the high efficiency behaviors that we've been constraining for here. And then we can take a look at its metrics. And so what we see here is we get the same power out that we expected. We get essentially the same loss ratio we expected. Frequency is very close. This is at 8 megahertz. The amplitude of resonance and maximum E field are very close to what we expected. And what's exciting about this design is it points to a capability of 3.6 watts per millimeter squared, which is quite high power density. That's about an order of magnitude higher than what the magnetic component could do in this particular space. Okay, so that's exciting to see. If we generalize this, then we can take a piezoelectric component and we can scale it by all 3 dimensions by scaling factor alpha, just like we did with magnetics in the beginning. And we can lean on the theory that we derived for these piezoelectrics to figure out what the scaling properties are. In this case, volume increases by alpha cubed, again, because it's volume. But the maximum power it can handle now increases by alpha squared. That's great news for going down in size. Power density rises. In this case, frequency also rises. So we've got to be able to accommodate that. But the minimum loss ratio stays completely constant. Now, as we go down in size, we would have to accommodate more loss, but these are encouraging scaling properties for miniaturization, especially in comparison to magnetics. So with that, we've shown that we can design piezo-based converters with high efficiency behaviors, wide voltage gain ranges, practical switch implementations with no additional energy storage components. Now, we've also shown that we can design piezo components then with figures of merit for materials and vibration modes and geometry conditions corresponding to maximum efficiency and maximum power density. When we do this, the resulting piezo capabilities scale favorably for converter miniaturization. So with that, we conclude that piezo-based converters show promise for high voltage, low power applications. Now, I've had the privilege of building and managing a team of 6, including me, students working on piezo-based power conversion over the past 3 years. A lot of what I've shown here would not be possible without their work. So I want to acknowledge them. Thank you very much. I'd love to answer any questions. I'll say I don't have a time in front of me, so if someone wants to.
No, we're doing great.
Okay, great.
Right.
Hi, great talk. Thanks so much, Jessica. Very, very interesting stuff on piezoelectric. I used to work on magnetics, so I have a similar question. Can you comment on nonlinearities and how they play into the efficiency considerations, especially at high frequencies?
Yeah, so the short answer is we don't know yet. This linear framework is the first framework really for evaluating what we can do. We do expect nonlinearity with respect to temperature. Going to higher power densities, I would expect something to be there, but the short answer is we just don't know yet. These are capabilities forecasted based on what we know now. But similar to high frequency losses in magnetics, I'm sure something will come about. We just haven't found it yet. Thank you.
All right. Make sure that that's still on. So you just talked about scaling. Give us some sense of range. Is it microwatts to kilowatts? I mean, how many orders of magnitude and roughly what's the range we're talking about?
Yeah, so let's see. With regards to scaling, I would say primarily at the lower power supply level and lower, especially as we go down to chip scale, is where we're going to see most of this advantage. Because as we go up in power, we're going to see the alpha to the fourth, the magnetics, get much more favorable. So piezoelectrics do not scale upward well. They only scale downward well. And so you could imagine a situation in which we use a whole bunch of separate little piezo-based converter cells to achieve higher power densities or something higher power. But that is going to get more and more, I guess, competitive with the magnetic component at that point. In terms of how far down we can go, it's a similar answer to before where we don't quite know yet. Everything we have right now is pointing to really the limits being manufacturing limits. If we're integrating something on chip or whatever it could be.
Thank you for the talk. I think it's very interesting. I have a question is for the work you presented, we have been developing based on an equivalent circuit model. And the application of this one is when you scale down the device. So can you comment on if as we scaling the device, do we expect any change in that equivalent model? And yeah. Just that.
We don't expect a major change in the model. I should say piezoelectrics are used at extremely high frequencies for other applications. And when I say extremely high, I'm talking about hundreds of megahertz, gigahertz, way higher than we use in power conversion today. And that electrical model still applies. Some of the things that we've seen that deviate from that are what we call spurious modes, which are essentially other vibration modes of the piezo making an appearance in the impedance spectrum, in the part of the impedance spectrum that we're interested in. But there's ways to avoid that. And so as we go down and down in size, we expect, of course, the model parameters will change, but we expect the same principle to apply. As long as we're operating it close to its resonant frequency in the inductive region. There's a very narrow inductive region in that spectrum.
Hey, Jessica, this is Pete Sauer. I was intrigued by the circuit that showed the transformer in it.
Okay.
And it made me think crazy things like solid state transformers.
Okay.
The elusive, the elusive device that replaces all that iron with lighter weight things. If you stack these up or something, is there a way you could, instead of getting smaller, think about going bigger and somehow using these together to create a useful transformer?
Yeah, so in terms of scaling, it's correct that if we want to scale to larger power, we would want several smaller cells operating just like this that are operating together. We would not want to scale this larger within itself because of the scaling properties and how that would compare think that there are potential capabilities and much higher powers if we're able to, first of all, with transformers, get their design to a point where they're competitive. Of course, right now, 90% is what we're looking at. But second, look into ways to highly modularize systems with different components consisting of them. Is what I believe that would have to look like for higher power.
Okay, I also wanted to ask about how small you intended to go with this miniaturization. Are you talking about clean room stuff at that level?
Yes. Yeah. Eventually, yes. That's where this is likely headed, and that's where this is likely to shine the most in comparison to magnetics. Because of the scaling laws, from what we understand right now, the smaller we go, the better. Even if we parallel things, even if we stack things, so the smaller we go, the better. So that's where we're headed. I don't have a complete answer on what the bound of that would be. But if we can do that, we think it would enable quite a lot.
Yeah, I have a defibrillator that needs a battery change. And if I had one of these devices that would be triggered by the heartbeat, maybe that would avoid having a battery change.
Yeah, so biomedical implants is certainly a place where this could shine. Now, we would want to go materials that are not lead-based, of course, but yeah, no, you're certainly right. Any sort of space constraining situation like that is where this would certainly shine.
Okay, thanks for coming this long way to talk to us.
Thank you. Good luck with the battery.
Okay, thanks.
Maybe one last question here. So coming from a resonant converter design, one of the questions that always comes up is tolerances and how it affects your resonant frequency and how design tolerant you are to that. So I guess the two-part question would be the materials you've tested with so far, what do the tolerances look like, especially when it comes to kind of that resonant frequency? And then design-wise, how dependent are you on that resonant frequency being correct?
Yeah, great question. So can I use this whiteboard? Great. So the impedance spectrum of this, oh, that's dead. Let's see. Okay, so I'll try to write large. Magnitude of impedance versus frequency. The impedance spectrum of this is going to look like one resonance and then what we call an anti-resonance. Okay, that's pretty bad. But basically, this is our inductive region. And within that region is where we operate. We're not constrained to right here. So we're operating somewhere in here. And depending on how high or low power we want, we modulate between the two, between the resonant and anti-resonant frequency. So what that means is that we are less sensitive to variation than applications requiring this resonant frequency. However, there is variation with the resonant frequency with respect to temperature. I think temperature is actually the main parameter here. And then of course, manufacturing tolerances, but we're less sensitive than some of the others. But that's something that closed loop control would help us with for sure. Now, in terms of the distance between these two, it depends heavily on that coupling coefficient, okay? And so this dictates then the distance between the two. So for a high coupling coefficient, which is what we want for high efficiency, we have a wide range here. So for some devices, this is 5 megahertz to 6.5 megahertz. So in terms of being able to land in the center here, somewhere in this inductive region to start, we think is pretty reasonable for a controller to do. Thanks. Yeah, or are we? Yeah.
Hi, thank you. Okay, so I didn't really know anything about piezoelectric devices before this talk, so thank you very much for coming. Some of the animations you used showed them moving. I was wondering if that's like just an animation, or do they actually move, and like by how much do they move, and does that affect when they're attached to the chip, like how, because if they're moving devices, I'm not quite sure how they're attached to like a chip.
That's a great question, and that actually hits on one of current challenges we're facing in general, current challenges for this going forward is how do we mount these things? Because yes, they are moving. They're not moving to an extent that the animation is moving. You can't see them moving. Hard PZT materials move significantly less than what we call soft PZT materials. But the strain can be somewhere between 1 to the -3 or so, so 0.001 and lower. So it's not much, but it is enough to think about if we're moving that much many times a second, what sort of loss is the mounting mechanism going to introduce, and how do we mitigate that? So that's something we're actively looking at right now. Now, PZT in particular has very high compliance, meaning it's, if you think about the stiffness constant for the spring, which means that there's a lot of ways to connect it with lower compliance or lower spring constant sort of apparatuses that wouldn't affect this resonance very much, but there's still loss to be considered in that. So to sum it up, yeah, the figuring out how to mount it is a question that we're still trying to answer, and it will be important for these.
We do have, I think, time for maybe one more. So if I might, you've taken a circuit model approach, as was pointed out. Presumably one could do that for any energy storage device and walk through the same kinds of time domain considerations and so on. Have you looked at that for switch capacitor, for magnetics, for batteries, you know, any energy storage device that could drop into a converter?
Yeah, I have not looked at it for other devices. I've thought about it in particular for LLC resonant converters, because that was my first project at MIT, and the performance of that ended up being pretty low. As you imagine, with a lot of resonant converters, we get away from the resonant frequency, we increase circuit or current circulation, which then gives us more and more loss. And so these sorts of mechanisms could be a way to get away from that. So I do think this sort of enumeration and figuring out how do we most efficiently utilize something is more broadly applicable, but we haven't looked at it beyond Piezoelectrics right now.
Well, we're at 10 minutes to the hour, so we're perfectly on time. So George, we're ready to wrap up.
Okay, I think she did very well, and she can meet all her other scheduled appointments this afternoon. So thank you very much, Jessica. Very interesting presentation, and very, very well done. We're very happy to have you do this presentation for us.
Well, thank you
And
so much.
that's it. See you guys next week. Thank you very much.
Bye.
All right, thank you. Really appreciate it.